the whole atmosphere community climate model. So as was just stated, WACCM goes up to 140 kilometers, which is in the mesosphere. And I'm going to talk about 5 fun things to do with WACCM. This is me actually operating WACCM on Bluefire with advice from Dan Marsh, who's the real rocket scientist. And I'm Mike Mills. I'm the WACCM liaison. This is how you can contact me. But if you need help, I prefer you go to this forum that Brian mentioned, which is bb.cgd.ucard.edu, which is for the entire CESM. And if you scroll down, there's a section for WACCM where people posted questions and other people posted answers. You can go through those and see if anyone else has run into problems that you're running into. And if not, post a new question and we should address it in a timely manner. So here's the 5 fun things we're going to talk about. How do I change model output? How do I change a reaction rate? How is the solar spectrum specified? How do I change a boundary condition? And how do I change an initial condition? And these 5 things are going to involve a lot of the details that Brian talked about, even as far as modifying the source code for some of them. So starting with changing the model output, you might want to add what we call a history variable to the list of things that are output in the model. Or you might want to create a new history output variable that nobody has output before. So the first thing you should do is look through the list of variables. And currently there's over 2,300 variables that exist in the model. So it's a long list, and in order to see the list, you have to actually have run the model once, because when you run the model, it creates this log file, atmosphere.log. And then a bunch of numbers for your run. So you look through this file and you do a search for this master field list. You'll see something like this, and it goes on for 3,000 different variables. And these give you some idea of the gases, CFCs, CO2, etc. So look through that. And the first case, you might want to add or delete an existing history variable. So there are a number of variables that are output by default. You might want to hit the history eraser button and delete that from the output to save you some space in the output. Or you might want to add new variables. You might want to change the frequency of the averaging of the output for these variables. Or you might want to create a new history variable. And in that case, we'll be modifying the source code and calling routines which are called add field and out field. And I'll explain those as we get to case 2. And then we'll need to recompile the model with this modified source code. So let's start with case 1. I want to introduce you to 2 cool cats that control history, Finkel and Fexel. And these are actually the names of variables in the name list for CAM. Finkel stands for file include, I believe, F include. Fexel is exclude. So there are a number of variables that get output by default. And if you don't want some of those, you have to put them in a list which is called Fexel. And if you want to add new variables, you have to put them in a list called Finkel. Now there are a number of Finkels and Fexels because there are a number of history file series in WACCM. And these are independent history series which can have independent output variables and independent frequency of output, independent averaging characteristics. So for example, there's the first history file series, which is by default monthly averaged output. And this goes by a name that looks like this. It has, you'll see an H0 in it, and then the year and month. And for some reason it says CAM2, even though we're pushing CAM5 now, but it still says that. And then you can add additional history series, H1, H2, and each of these has its own Finkel and Fexel in the name list. But there's this ironic convention where what's called Finkel 1 is for the H0 files, Finkel 2 is for the H1 files, and Finkel 3 is for the H2 files. So keep that in mind, subtract one or add one as appropriate. So this is what the name list for CAM that's relevant here looks like. You have a section with a number of variables that control the averaging and the output for each of these history tapes. So the first one is average flag per tape. And you'll see here we have 5 different averaging flags. That means we have an H0, an H1, an H2, an H3, and an H4. And the H0 files are averaged. The H1 files are instantaneous, etc. So the other valid flags are X for maximum, M for minimum, and then there's a B flag, which case you're averaging only at the same local time each day, which is midnight Greenwich Mean Time. So then for each history file, you have to have a Finkel for which fields you want to include. And you'll notice some of these have a :B, so they can vary from the standard averaging flag. So here we're looking at Finkel 3, which is instantaneous except for these guys, which are Greenwich Mean Time, midnight local time. And then each one also has Fexel, which is Finkel's evil twin. We also have this variable mfilt, the next one, which is simply a list of how many time series you're going to put in a given history file before you go on and create a whole new file. So, for example, the H0 files, you have just 1 month per file. So each month is a file. You don't have multiple months per file. But for the other ones, you can have, in this case, 365 times in one file, or 30, etc. And then finally, the NHT-FRQ is the history frequency for each of these. And these can be positive or negative. If they're positive, the frequency is the number of time steps that output is put out. If it's negative, it's hours. And then the H0 file can also be set to 0 for monthly averages. The H0 files are the only history tape that can have the monthly average. So 0 is only valid for this very first value there. If you want to change output in a run that's already started, you'll need to consult the CAM user guide on how to set up a branch for that. So if you have a bunch of things you want to add to the name list on a durable basis, you can create a file called usernl, and you stick it in this source mods/source.cam that Brian mentioned. And the model will pick that up and use that the next time you reconfigure. You need to first, if you've already configured the model, do a configure-clean name list, followed by configure case again. And then after you've done that, you want to check the name list that was created. And that is in the root directory, or the case directory, under case docs, there are name lists for each component. So there's one that's called ATM in, and in there you'll see the entire name list, which I've only shown a part of here, but it will include all those Finkels and Fexels, etc. So now how do you create an entirely new history variable. You have to modify the source code to add the calls to these two new routines that govern history variables. The first one is called add field. Add field is only called once when the model is set up at the beginning of a run, and it adds a new field to the master history file list, and you can give it a name there. So subsequently, you want to call out field, which will accumulate or take the minimum maximum as appropriate of each input field in the history buffer for each appropriate tape. And so out field is called at each time step, where add field is called only during setup. So out field can really be put in a number of different places in the source code, a number of routines, wherever you're calculating something, and it may be a new gas, or it may be a heating rate, it could be an ionization rate, a number of different things that can be output from the model, and wherever it's convenient for you to calculate that is where you'll call outfield. And Brian covered putting them in the source mods directory, and then following that you recompile with the modified source code by executing the build script, which is in your case directory. Now, what if you want to change chemistry? Change a reaction rate is the simplest thing to do. There's a chemistry preprocessor which actually generates Fortran code for CAM to solve chemistry. And it takes as input a simple ASCII file, which is shown here in simplified form. And it has a list of species. You'll notice here things like O singlet D with an arrow to O. What that means is telling the chemistry that the molecular weight of this species is the same as atomic oxygen. O2 singlet S is O2, molecular weight. And then you have two species that are fixed and not affected by chemistry, N2 and M, total atmospheric density. And then you have different classes of chemistry. You can solve them explicitly or implicitly. And then finally you get to the reaction rates. There's a bunch of photolysis reaction rates listed and then other reaction rates. So we're going to focus on this last part, which is bimolecular, trimolecular reactions and how you modify those rates. So you can look in this directory for a number of sample input files for the chemistry preprocessor, and there are dozens of them, and get an idea of how they're set up and grab one of those to modify. So there are four kinds of reactions that are in this section of the input file. The first is temperature-independent reaction rates, and that's just a fixed rate of number cubic centimeters per molecule per second. So here's an example of that, and this is the value of the fixed reaction rate in those units as it would look in the input file. The second is the familiar Arrhenius type reaction, which has a temperature dependence, A naught exponent B naught over T. And if you use the JPL values, for example, B naught is listed as negative E over R in there. So in this case, here you just have A naught and B naught following this reaction in the input file. Now there's what's called a TRO rate constant, which is considerably more complicated. And I won't go through all those details, but I'm showing them here. There's an A naught, an A1, a B naught, a B1, and an exponential factor. So these 5 factors are listed sequentially in that order in the input file. And you'll note at the beginning here we've given this reaction label, which is actually used in the source code as the name of that reaction rate. And then finally, you can have any arbitrary reaction rate you want, a user-specified reaction rate, and for this you just give it a label, you don't put any numbers there, and then you modify this subroutine user RXT, and you'll see in there a number of user-specified reaction rates, and you can just add yours for this label that you add. So once you've done that, you need to build the model with this new input file. So first thing first is to modify an existing input file from this directory that I showed before. You might find something in there that you want to modify, and so you should copy it to your case directory as a new input file, and then edit it with whatever editor you want, and edit Emacs VI. And then edit this XML file, which is for configuration, env-conf XML. And what you want to add in there is this option, user mech in file. So here it is at the end, where you have CAM configure options. And so you put this flag in, and then the path to your input file. So then after you've done that, you just reconfigure. You can do it, if you configured it earlier, you can do a configure clean all followed by configure case, and it should pick up that new chemistry. Okay, next question, how is the solar spectrum specified in WACCM? There are nameless variables that point to two files that specify the solar forcing. The first one is called the solar parms file, and this has geomagnetic and solar parameters, F10.7, KP, AP indices, that are used for aurora upper boundary conditions and generally wavelengths shorter than Lyman alpha in calculating heating rates, etc. And so if you were to grep the name list for that solar parms file, you would see where it is. And this is an example of that, and we'll look into that in the next slide. And the other file is called the solar data file, which covers wavelengths longer than Lyman alpha, and it has time variation of the total solar irradiance, or TSI, as well as variability with wavelength, which is the solar spectral irradiance, or SSI. And we'll look in detail at what that looks like, but that's also in the name list as a path. And both of these are input files that can be time varying. So here's the first one, the solar parms file. Remember, it has F10.7, KP, and AP. And this is a very simple solar parms file that just keeps all of these values constant at a value that there are during solar maximum. So what you need is, first of all, a list of dates that the model will interpolate between. So since we're keeping this constant, we want it just to have a beginning and an end point, and then all the data are constant at the beginning and the end point. So everywhere in between, they will be constant. So what this endpoint is the year 2200 0101, and the first one is day 101. So, which I believe is January 1st.
Year, month, day, day.
Year, month, day format. So you can have a time variation of solar cycles, and we have those input files as well, which have considerably more dates and considerably more different KP and AP. And those would be a much longer file.
So this example shows year 2200?
No, that example shows a run with a fixed set of solar parameters that are set to be a constant solar maximum condition. So what this is saying is that all dates between the year 0 and the year 2200, these are going to be the values, because this is the value at the beginning and this is the value at the end, and in between you interpolate. So the next file is the solar data file, and this is generally longer. It has total solar radiance as a function of time in watts per meter squared, solar spectral radiance as a function of time and wavelength, and you can have a number of wavelengths. In this case, we have 3,780 wavelengths covering most of the spectrum, wavelengths longer than Lyman alpha.
So if we want to do realistic events, we're never going to actually have to alter these files, right?
If you want to do historical events, you don't have to alter them. If you want to do some simulation over many decades, where you repeat maybe one solar cycle or 3 solar cycles, you might need to modify it. But if you want to, you might have to pick which file you want to use. So you might want something with a constant versus a varying one.
Do you guys then, every year or something like that, create a new set and then make it available on the web?
Yeah, we try to update this as fast as we can get the data added to the queuing.
Yeah.
So it's all, usually that's where we're getting our spectrum from. But, there are other solar physicists that have other spectrum that they want to try out more.
They disagree with you, so they built their own.
Yeah.
And so right now, I think we're going through the end of 2005, and we have daily varying TSI from the mid-20th century, like 1960 or something.
Does WACCM correct for, are these at Earth or are these at 1 AU, and then you correct for the ellipsis?
This is all at 1 AU. Okay. And then the orbital geometry is taken into consideration.
Okay.
In terms of updating stuff like, say, Einstein coefficients in case of hydroxyl radical, is there a set schedule for that you only do it every 3 months, or?
Well, we usually try and keep up with the JPL thing, but we can't. We are documenting the scientific state of the model in papers. So when we'll have a series of papers on this version where we'll tell you that it's current to JPL 06. If you're worried about a rate, Mike just told you how to go in and update it, and you can see how sensitive it is to that.
My eyes always get wide when I hear Einstein coefficients, sorry. So you can play God with these 2 files and modify them, and then there was light. Next, how do you change an initial condition? Well, first you want to copy an existing initial condition, and if you look in the name list and grep for this variable, nameless variable, NC data, that's the path to an initial condition file. So you'll see something like this: path to input data, atmosphere, WACCM-IC, and then the name of the file, and then the year at the end. It'll be something with a .I in it to tell you it's an initial condition file. So you can go there and you can copy it and create a whole new file that you can modify. So then, to modify it, you can use your favorite NetCDF editor, which could be NCL, which is NCAR's own, or NetCDF operators, NCO, I believe also developed at NCAR, or IDL will do that, developed here at LASP. And here's a quick 2-line example of how to scale the CO2 in an input file. This is using one of the NetCDF operators called NCAP, NetCDF arithmetic processor, I believe. And this is something Dan sent me, and I'm trusting him implicitly here. But if you do this, he says you are scaling the CO2 by a factor of 0.883, but unfortunately, for some reason, it strips out the units, so you have to add them back in with this second NetCDF operator.
It's just a quirk of the NC operators, I guess. And this is how I created a CO2 atmosphere for the 1850 control to the present day, and I just scaled it back.
So,
And I did this with a lot of other variables, but this is all I did to get an IC for the 1850. Then we ran it for a couple of hundred years, and what you get is the end of that as your IC. So it's equilibrated, but this was our first crack at scaling back to 1850.
so if I remember correctly, it wasn't too long ago where people were having troubles doubling CO2 in WACCM, but now are we saying we can do it? We just do this, multiply by 2?
We could do it, but you'll have to go read the literature and determine whether or not the parameterizations for CO2 cooling, which we get from Victor Formichev, are valid for double CO2. I think they probably are, but you can do anything you want, whether or not you're going to get scientifically.
Right, I think when we were trying to double it, it crashed. That's why I was asking. It's not like it gave unreasonable results, it just didn't line up.
Yeah. So whether or not you might have to get there by steps, I don't know, probably 25% safer. This is more of a scientific question. I mean, this is sort of whether or not.
Yeah, no, I thought that it just the mechanics of it didn't even work, but it.
It could very well be that you put such a shock to the system that it was numerically unstable.
And then you have to go and modify the name list. So to update the NC data variable to point to your new file, and then finally run as an initial run, not a restart run, not a branch run, using this new set of initial conditions. So that basically covers the 5 things to do with WACCM: how to change model output, how to change the reaction rate, how the solar spectrum is specified, how you change did I cover? I didn't cover boundary. Okay, 4 things you can do with WACCM. And how to change an initial condition. It's considerably easier with the new CCSM scripts than I think WACCM 3 was. So as Brian said, it's not rocket surgery. All right. Thanks.